So to relate clustering and clustering methods to what we have looked at so far, I start with the claim that clustering is something like classification without labeled data. So it's an unsupervised method. We call clustering methods unsupervised because these methods don't need any labeled data. So you don't need any labeled training data for clustering methods, which is nice, practically speaking. Let me show you one example, which I have worked on recently for city planning department of Helsinki. They are interested in having somewhat real-time overview of the conditions of pedestrian crossings in Helsinki. And what they can do easily is they can download all pedestrian crossings that are documented in their database. And this data is free, so I have shown here the web address. I can also share a Python notebook that shows you how to read in all the pedestrian crossings or all the snapshots of pedestrian crossings that are available throughout city of Helsinki. So you have a bunch of data points. So what could be one data point here in this example? Yeah, there's one comment. Data could be a color or a pixel or a picture. Yes. So remember, data, we use data in a very abstract sense, which is powerful, but also requires to specify what we mean by data. And in the most general sense, data is a collection of similar units of information. And what is here the elementary unit? And we have a lot of similar units where we have these pictures of pedestrian crossings. So I would say one data point is one of these pictures. So we have a bunch of data points. What do we use to characterize data points typically? Features, yes, exactly. So what could be features for one such data point, for one such pedestrian crossing, or one such image of a pedestrian crossing? What could be a good feature? The color, well, we could stack all the pixels. Let's say this is a 100 by 100 pixel image. We could stack all the pixels, red, green, blue values into a long vector. Then we get a vector of length 10,000. So this is quite long, and there are efficient methods to automatically find out the few features. We will hear about such feature learning methods in round 6. I just show you here the result of one such method, where each dot here, each blob, each blue dot here corresponds to one of these pedestrian crossing images. So I have shown here one such image corresponds to this blue dot here. So I have used some feature learning method, and we will hear more about feature learning methods in round 6, and turned each of these 100 by 100 pixel snapshots into two numbers, feature 1 and feature 2. And those, if I use only those two features to represent data points, I can plot them nicely in a two-dimensional plane as a scatter plot. Okay, so we have data points. We have found some good features, two features for them, but we don't have labels. The city planners of Helsinki, they don't have any labeled data. Nobody there has worked out, or not yet. For example, they could hire a summer intern, which looks at each pedestrian crossing and says this is a good crossing, or this is not this crossing needs maintenance. But they don't have it yet, so they don't have labeled data. They just have data points. So what can we do with such unlabeled data, with just a bunch of data or data set? Well, clustering methods can be applied to such data sets. Clustering methods try to group the data points into groups or clusters which collect data points which are more similar to each other than to data points in other clusters. And I just show you the result of such a clustering method. So this clustering method I applied in Python found that there are two types of pedestrian crossing snapshots, two types of data points here. there are one type of data points which are on the periphery, on the outskirts of this cloud, of this point cloud, and there are many, many, many other data points inside this point cloud. So I would say then on the outside or on the border, these are outliers. So I have found using clustering methods some of these pedestrian crossings which look somehow different from each other. And now what I can do is I can look at the snapshot, so I know which data point this is, and I know which pedestrian crossing this was. And here are some of these outliers. And you see what these clustering methods found as outliers indicate pedestrian crossings which don't look that typical. For example, there are shadows, or the paint is not very clear anymore, or not very shiny anymore, or there is a roof nearby which makes it somewhat difficult to observe the pedestrian crossing. So it gives us a reasonable collection of pedestrian crossings which are not typical, and which might need maintenance. So somebody would need to go there and renew the paint there. And this has been done. So this is a machine learning method, or an application of machine learning method, without any labeled data. So nobody looked at the pedestrian crossings manually and classified them. Good pedestrian crossing, not good pedestrian crossing. So there's one question: which features have been used for clustering? Yeah, these are two features that have been found by a feature learning method. We'll talk more about feature learning methods in round 6. But for the time being, just believe me that I have used a feature learning method that found two good features. Okay. So, but then I would like to focus on another example for a data set more throughout this lecture, which is even more simpler data set, and it's one image. So you can look at one image as one data point within a collection of images. For example, I took a lot of pictures during my hiking holiday here, and this could be one data point. Or I could say one image is a whole data set, and the data points are patches. So I cut this image into smaller patches and consider each of these patches as a data point. So this should show you that it's really a design choice what data points are. A data point could be a whole image, or a data point could be a part of an image. It's up to you what you would like to do. And here I would like to show you how we could use clustering methods to do a foreground-background segmentation, to segment the image into different parts. For example, we have here the foreground scene with a lot of trees, with a lake, and in the background we have the mountains. And we will see how we can use clustering methods to separate these components of an image in a very simple manner. And for this, we define a data point as one part, one patch of the image that we would like to find out. Is this patch more belonging to a background or to a foreground? Okay. Yeah, so what are the features of one of these data points? So what could I use as features of one such data point, one such patch, which I have shown here? Yeah, the same as before. So a patch of an image is also an image. It's a part of an image, but we can also consider it for itself, and it's an image. So I could use the average green, red, and blue component, and this is what we've done here. So one of the teaching assistants created a Python notebook which computes the average for each patch, for each data point, the average red component, the average green component, and the average blue component. So each one of these blue dots here corresponds to one patch, and this dot is located in a three-dimensional space corresponding to these three color components. So the color components, the three color components, are the features of the data point. Yeah. But I would like to have it even simpler, so I only use two components. I only use the red component of a patch and the green component of a patch. Do you think this is a good idea to use these two features in order to find the foreground of this scene, of this hiking scene? Do you think it's a good idea to look at the average redness and the average greenness of these patches to find those patches which correspond to the foreground? Yes, why? Why do you think they are reasonable, these features? Well, intuitively, in the foreground there's a lot of forest, a lot of green, so the greenness could be a very good indicator. So the greenness of a patch could be a good indicator if this is more a foreground component or a background component. And we will see actually that this works. So now I only use these two features. So each orange or light red blob or dot here corresponds to one patch. So I've shown here one patch, which is more a foreground patch, and then another patch, this here, this dot, which is more a background patch. And we see that this foreground patch is more, in the region with more greenness, with higher greenness values. And we would like now to separate this into two components. So this corresponds to all patches, to all rectangular patches of the image, and we want to somehow group it into two clusters. And this is exactly what clustering is about. So clustering is about, according to a dictionary, just a definition which I grabbed up, a group, we want to find groups or a group of data points, which is called here discrete items that are close to each other. So we want to group those data points into clusters such that the data points within the cluster are more close to each other than two data points in the other cluster. However, this definition here that we have used so far, using the word close or close by, is not precise. So it's not a mathematical definition. We need to make this precise and define what we mean by close by. And again, here comes a design freedom into play. So the notion of close by is a design choice. However, many methods and a very widely used choice for this close definition of close by is based on the Euclidean distance. So the distance that we see here in this scatter plot. So those two data points are more close to each other than, for example, this and that data point. But this is only one option for defining the notion of close by. We could also say two data points are close by if they can be reached via hops between near data points. And this notion of close by is used by a method called dbScan. And you will use this method dbScan in the coding assignment, if I remember correctly. But today I will only talk about clustering methods which are based on the Euclidean distance. So we group data points into the same cluster if they are more near to each other in the Euclidean distance. Are there any questions up to this point? So let's start with maybe the most popular clustering method, which is called k-means. And this is a hard clustering method. By that we mean that each data point in a hard clustering method, each data point is assigned to one and only one cluster. So if we say we want to break this into two clusters, then each data point belongs to either of two clusters. There are also soft clustering methods, and we will talk later about a soft clustering method, which assign each data point to several clusters with different degrees of belonging. There's one question, how about outliers which don't fit any clusters? So how to handle outliers? This is again a design choice, and one option would be to not fix the number of clusters, like in the method dbScan, but define a minimum number of data points that we require to be inside a cluster. And if there are some data points which are not ending up in a cluster, they are declared as outliers. So dbScan provides such a method to define outliers. But I will not talk more about this today. Okay, so k-means is a hard clustering method. Each data point is assigned to one and only one cluster. And the key idea behind k-means is to represent the cluster by a cluster mean. So a cluster mean is just one potential feature vector, one here, this green feature vector, and here this red cross. And these two feature vectors are cluster means. So we have two clusters, one cluster with this cluster mean, and this cluster, another cluster with that cluster mean. So once we have this cluster means, how do we assign the data points to the clusters? What do you think? What would be a reasonable choice? So if I have the cluster mean for cluster 1 here, and the cluster mean for cluster 2 here, how do I decide if this data point belongs to this cluster or to that cluster? Yeah, very good. So you already guessed it. We just compute the distances. For each data point, we compute the distances to the cluster means and assign the data point to the cluster whose cluster mean is nearest. So it's pretty intuitive, it makes pretty much sense. So here I have shown the distance or the kind of the interval between those two clusters, or the section between those two clusters, or the line segment connecting the two cluster means. And in the middle, we divide the space into those data points which are more near to this cluster, and the other half space containing the data points which are more near to the red cluster mean. That's called a cluster assignment. So we now color all the data points which are more near to the green mean by green. So this is the green cluster and this is the red cluster. Okay. Yeah, there's one question: how are the cluster means obtained? The first cluster means we start with initial choices. So there are different options. For example, use randomly chosen cluster means. There are different choices for how to initialize the cluster means. Another option could be to randomly select two data points as cluster means. So somehow we have this initial cluster means. Okay, so after we have the initial cluster means, we update the cluster assignment, and now we have a clustering. So are we now done? What do you think? We now have a clustering. Are we happy? So we could now output this clustering. For each data point, we know if it belongs to the green cluster or to the red cluster. However, now the cluster means might not be the actual average of the data points because we updated the cluster assignment. The first choice for the cluster means were somewhere arbitrary, and they led to this cluster assignment. And what we would like to have is that the cluster mean is actually the average of the clusters. So after we update the cluster assignments, we have to recalculate the cluster means. So now the cluster means move. And now, since the cluster means have moved, what might happen? So are we now happy? Are we now finished? Yes, there might happen that now, since the cluster means have moved, the distances between the cluster means and this data point, for example, this here, might have changed in such a way that this data point here changes sides. So this data point becomes now more near to the green cluster mean, so it becomes a green data point. Okay, so we need to update again the cluster assignment. And if we update again the cluster assignment, we have to do afterwards, update the cluster mean again. And that's what k-means does. So it iterates those two steps until some criterion is met. For example, one criterion for checking finished or declaring finished is a fixed number of repetitions of these two steps. So you could say, so this of course is implemented in a scikit-learn object, which is called k-means, and here you can choose the maximum iterations. So let's see if we get the pen here. So this max iter defines what's the maximum number of repetitions we use in k-means for the cluster mean and the cluster assignment update. Yeah, and here also in this k-means object or class, you also see a parameter for the initialization. So here with this parameter, you can choose different strategies for choosing the initial cluster means, so this init. But for details, I refer to the documentation of scikit-learn of this Python library. Okay, that's pretty much about k-means. It's maybe the most popular clustering method, and I would say one of the top 5 or even top 3 machine learning algorithms. This is a very basic, very simple, but very powerful algorithm. Okay. Yeah, so I have now implemented, or one of the TAs has implemented this k-means clustering method on these data points representing the patches or the small parts of an image. And when we then color the patches according to the clustering result, we get this output. So the green ones, these green patches correspond to these green data points, and the reddish parts of the image correspond to this red or orange data points. And we see that the clustering actually pretty well got the foreground, which is made up of the forest, the trees, and the lake. So there's one comment. Yes, the number of clusters is predefined here. So we choose the number of clusters, k equals 2. That's also the argument here in this Python object. So the number of clusters, this n clusters, this is the k equal 2. Yes. So we fix the number of clusters. So now I'll show you a concept that allows, for example, to choose between different numbers for the clusters, or to find a good choice for the number of clusters. And this can be done by using a quality measure for how good a clustering is. And again, this is quite intuitive. We can define the quality of a clustering or the clustering error by saying what would happen if I replace the data points in each cluster just by the cluster mean. So instead of this data point, I would just use this cluster mean. And the error that you make is simply the difference between this this data point and the cluster mean. And we compute then the average distance or the average errors over all data points in each cluster, and then also average over all clusters. And what we get is the clustering error. So this is the average distance between the data points and the nearest cluster mean. And this quantity, this clustering error, you find as the property or the attribute called inertia in the Python object. I guess in the coding assignment you are required to analyze or determine how this clustering error changes for different number of k, so for a different choice for the number of clusters. But besides allowing to choose the number of clusters, this clustering error also provides us with a tool to check when we can stop the iterations. So the when we can stop repeating the cluster means update and the cluster assignment update, because k-means turns out to be an optimization method that iteratively minimizes this clustering error. And at some point you will hit the floor, so where you will not reduce the clustering error much more. And then you can define, so when this clustering error drops only very little, with increasing number of repetitions, then you might say, okay, now I'm finished. So we can use the monitoring of the clustering error as a termination criterion for k-means. Another option is, as I said, just use a fixed number of repetitions of cluster means update and cluster assignment update. Okay, so this was all I wanted to say about hard clustering method, k-means. Are there any questions at this point? There's one question. If the clustering error after the iteration is still large, should we rerun with more clusters? Yeah, so what you do with the resulting clustering error depends heavily on the application. So if you want to segment your image into foreground and background, then you have intrinsically two clusters. So there is no, it doesn't make sense to use more clusters. But when your goal is to use clustering for compression, you can use clustering for compression by replacing each of these data points by this cluster mean. So instead of transmitting this image patch, this data point, you just transmit this cluster mean. And there, it might be useful to increase the number of clusters if the clustering error is too large for the first choice for number of clusters. Yeah. Okay. Any other questions? Okay. So now I talk about the second clustering method in this lecture, which is a soft clustering method. By soft clustering, I mean that a data point, for example, this here, is not assigned to one and exactly one cluster, but to several clusters. And for each cluster, we define or determine the degree of belonging by which this data point belongs to this cluster and to that cluster. And this is useful when you have boundary case or border cases like these two, because these two data points, for example, they are not so clear cut in either of these clusters, but they are somewhat border cases. And using the degree of belonging allows to define or to characterize these border cases, because for these data points, the degree of belonging will be pretty much the same for this cluster and for this cluster, whereas for this data point here, the degree of belonging to this cluster will be much higher than the degree of belonging to this cluster. So using the degree of belonging allows us to explore the if a data point is more a boundary or border case or really inside a cluster. Okay, but I want to illustrate soft clustering first by another data set where a data point corresponds or represents a country. And we're interested in the country, how well a country did during the COVID-19 pandemic. So what we use as feature is we use the average increase of infections in percent over the last, say, 30 days. So we can get such data. I have shown here a snapshot from Wikidata. You can download this data, and then you can represent this data set as a one-dimensional point cloud. So the location is given by the feature X. For each data point, we have the feature X, which is the average increase of COVID-19 infections in percent. And here we would like to find out, how many different clusters are there, or are there clusters of countries where the pandemic behaved fundamentally different to other countries? And here it might be useful to represent the cluster not by one cluster mean, but to have some soft clustering where we specify the degree of belonging, so by which each data point belongs to a certain cluster. And we can do this, we can obtain soft clustering methods by using a different approach to representing a cluster. Remember, in hard clustering, we represented a cluster, a single cluster, by one mean vector. So for example, in this case, one cluster, in k-means, we represent one cluster here by one value for x. For example, this here. So this here could be one cluster mean. And this is all we use to represent the cluster in k-means. So there's one question, can you have recursive clusters? So cluster within a class. Yes, so there are also different clustering methods which use a recursive cluster structure. So you group clusters into more fine clusters, which is called hierarchical clustering, but I will not talk about hierarchical clustering in this lecture. Okay, so the key idea behind soft clustering methods is to represent the cluster by a distribution. in particular by a probability distribution. And we interpret the value of the probability distribution for a certain data point. So this x here is the feature of a certain data point, and we can evaluate this distribution. This gives us a number, and this number we interpret as the degree of belonging. So this might look a bit weird to represent a cluster by a distribution. In this case, we will represent it by a Gaussian distribution, but it will turn out that this is very useful, a very practical idea. So a single soft cluster is represented by a Gaussian distribution here, which in turn is characterized or fully determined by two parameters, by the mean mu and by the spread or standard deviation sigma. Sigma squared is also known as the variance of this distribution. So we use two parameters, mu and sigma, to characterize this distribution function which defines one cluster. So instead of using only one, we can interpret k-means as the special case of this approach by setting sigma always to 0. So we characterize one cluster only by the mean vector mu, which is the cluster mean then. But in the soft clustering method, we spread out the distribution a bit. So we use a non-zero sigma here. Now the question is, okay, yeah, I can represent the cluster by a Gaussian distribution. Sure, I can do this. Why not? Nobody keeps me from doing this. But why is this useful, and how can this be useful? Well, we need to find a way to somehow match such a distribution to data. So how can we find, given such data points, how can we find a good choice for the mean and for this standard deviation of the distribution? Does anybody have an idea how we could find good choices, or how we can learn a good value for mu and for sigma given some data set? So remember, this distribution can be is a special case of a probability distribution, and this probability distribution is determined by two parameters. So how can we fit the parameters of a probabilistic model or a probability distribution to given data, which we interpret as realizations of a random variable? Did any one of you had a course on statistics or estimation? Well, one natural way or useful way is to use sample means. So the average is the average of the data points or the features of the data points. So this here are the features. This here is the feature of the ith data point. And we can measure the variance, so the spread squared, by the sample variance. So this is known as the sample variance. Okay. So this is well established, and there's hundreds of years of probability theory, which contains very useful results that tell us that these estimates are very good choices for the parameters. So using these estimates gives us a very reasonable choice for mu. So we approximate mu with mu hat, and we approximate sigma with sigma hat. So this is how we can fit one soft cluster to, or one single soft cluster to data points. What about several? So we often want to have more clusters. Well, we then have to introduce weights. So we then model with two clusters, we model the data set as realizations of a random variable which belongs to a mixture of Gaussian distributions. So this mixture or mixing weights are P1 and P2. these are numbers, parameters again, which have to sum to 1, because we want this mixture of distributions to be a valid probability distribution. And valid probability distribution has to sum or integrate to 1. That's why we need to require these weights to sum to 1. Okay. Yeah, and this sum of these two Gaussians, this weighted sum, so we take this Gaussian distribution multiplied by P1 plus this Gaussian distribution multiplied by P2. This is known as a Gaussian mixture model. Gaussian mixture model, or Gaussian mixture as a sloppy abbreviation, Gaussian mixture. Okay, and we can have also more than 2. We can have any finite number of Gaussian components. So the fitting, how do we find these parameters given a data set? This is now considerably more difficult than the single cluster case where we just used the sample or the averages. In this case, we need to use advanced methods for fitting a probabilistic model to data. These methods are known, for example, as expectation maximization, but this is way beyond the scope of this course. We use, of course, Python. So this is one line of Python code. In particular, this line here, fit, this line here does the job and finds a good value for sigma 1, a good value for mu1, a good value for mu2, and a good value for sigma 2. So this happens when you use this function Gaussian mixture.fit. It determines the parameters of these Gaussian mixture components. Okay, and yeah, so far we considered soft clustering only using a single numeric feature, x, but for this image segmentation we had 2 features. So we had here I think this direction was the greenness of the data point, the greenness, and in this direction we had the redness of the data point. So we use now a 2-dimensional Gaussian distribution, which I indicate here by this ellipse, to represent a soft cluster. So a soft cluster is a multivariate Gaussian distribution, which is characterized by a mean vector, which is now a 2-dimensional vector, and a covariance matrix. So instead of a single variance, we have now a covariance matrix, and I have shown here the eigenvectors of the covariance matrix. So these are the eigenvectors of C. Okay. Yeah, and again, I can have more than one soft cluster, in particular 2 soft clusters, if I want to separate into background and foreground. And yeah, how do I get the parameters for these 2-dimensional Gaussian distributions? It's again the dot fit function. So the dimension here is determined implicitly by the dimension of this NumPy array. So you don't need to tell Python what the number of features is, because the number of features here is implicitly defined by the number, I think it's the number of rows or the number of columns of this NumPy array, which holds the feature vectors of the data points. So these are the feature vectors. Feature vectors. Okay. This is soft clustering. So to wrap up, I have talked about 2 clustering methods today, maybe the most widely used and most basic clustering methods. One is a hard clustering method known as k-means, which assigns each data point to 1 and exactly 1 cluster. Then I have discussed a soft clustering method using Gaussian mixture models. The difference between those 2 methods is the way to represent the cluster, whereas k-means represents a cluster by a single feature vector or a mean vector. In soft clustering, we represent the single cluster by a mean and the covariance matrix, which are the parameters of a Gaussian distribution. And this allows us to define, for example, degrees of belonging by evaluating the value, by evaluating the Gaussian distribution function. There's one question: what are the two soft clusters? Same kind of data sets fetched from two sources. So these two clusters here, if the Gaussian, these are drawn by hand, so I'm not sure if exactly these will be found or might be found by the Gaussian mixture model method in Python. These two clusters correspond to the foreground patches, which have more green because they show trees, and this is the background. These are the background patches. So these are the data points are from the same source. The source is the data source is this image here of the hiking scene. So all the data points come from the same data source. This image here, big image, is the data source, but they form two groups which differ in their colors. Okay. Yeah, and I want to highlight that these two methods that I discussed today, they are based on the Euclidean distance. So they use the notion of Euclidean distance. For example, here, those two data points are close by because the distance is small, whereas this data point is not close to this data point because the distance is large. There are other notions for close by. For example, dbScan, the method dbScan uses another notion for close by. Okay, that's it from my side. Are there any questions? So there's one question on in which situations we can decide which clustering method is more suitable. There is no general rule for that. As I said, it depends on the application. If you're interested, for example, in this image segmentation application, so soft clustering, if we would use soft clustering, we could use different levels of green and red component to make this transition between foreground and background smoother. So using a soft clustering would allow us to modulate the greenness and to make it make this transition more smooth or soft. So it depends if the customer wants a soft clustering or not. So mathematically, there is no rule that allows to tell for this application you need hard clustering or soft clustering. They provide different services, so to say, for the customer. Some customers might be interested in having a degree of belonging to clusters, and in some applications it's not relevant what the degree of belonging is. Okay, any other questions? If not, then I close this lecture. Thanks a lot, and I will put the recording online as soon as possible. Thanks, and have a nice evening.